The empirical rule is a rough guideline, a rule of thumb that says if a distribution is unimodal and symmetric, so if it's a normal curve, then approximately 68% of the observations will be within one standard deviation from the mean. So here we have the mean in the center. Between one standard deviation above and below, 68% of the observations lie there. Approximately 95% of observations are within two standard deviations of the mean. And nearly all, or 99.7% of the observations are within three standard deviations of the mean. And then this image has all of the different areas marked off even more specifically than that, which we've calculated before. If you take the 68% and cut it in half, that's how you arrive at those two 34% chunks in the very center. And then you can go out to 95%, basically subtract off that 68% in the center, figure out what those other two slices have to be, and on out and on out. So knowing all of these different percentages, though, is really important. It's something you want to basically memorize. All of these different sections, because when you use the empirical rule to find probabilities, you could be asked to find sort of any combination of these different percentages. We also know that any values that fall outside of two standard deviations from the mean are considered unusual because only 5% fall that far out, 2.5% on either extreme. So that is anything outside of here and here are considered unusual. Because again, there's 2.5 total percent out here and 2.5% going this way from this two standard deviation mark outward. Now, z-scores are calculated by taking the value that you observe minus the mean and then dividing that by the standard deviation. And all that tells you is how many standard deviations this value falls from the mean. The z-score is also referred to as the test statistic. It's really hard to say, test statistic. And you can calculate these z-scores and convert basically to a standard normal model where appropriate, where you calculate what is the mean in the center 0 and how many standard deviations counting 1, 2, 3, or -1, -2, -3 out on either end. So let's use the empirical rule to find some probabilities. We're told that women's heights are in fact normally distributed, with a mean of 64 inches and a standard deviation of 3 inches, and we want to use the empirical rule to find various probabilities. What I suggest is drawing out a normal curve, a bell curve, for this situation and labeling all the parts. So it's not a really beautiful looking one here. You can do better than me. But we know the mean is at 64, and then we know if we go out 1, 2, 3 on the right, and 1, 2, 3 on the left, we should be counting by 3 inches each, since that's the standard deviation. So let's see, we would have 67, 70, and 73 here, and then let's go down, we would have 61, 58, and 55. And then let's remind ourselves that, remember, between one standard deviation is 68%, within two is 95%, within three is 99.7%, and then we can even mark off all of these smaller values. This is 34%, 34%, 13.5, 13.5, 2.35s, and 0.15s. If you can remember that, you can answer any question, any normal curve, empirical rule, probability question that they could ever throw at you. So the first one asks us, what's the probability that a randomly selected woman is between 61 and 67 inches tall. I can look at my normal curve and say, well, that is just within one standard deviation, so 68%. What's the probability that a randomly selected woman is less than 70 inches tall? That would be everything from the 70 mark and backwards. So I could add up basically all of those probabilities. I've got a 0.15 plus 2.35 plus 13.5 plus 34 plus 34 plus another 13.5. So if I add all of that up, it's the same thing as if I took 1 minus, basically, or if I wanted to, an easier way would just be to do 1 minus the 2.5. So it's everything other than that. So it looks like it's 97.5% probability that you would be less than 70 inches tall. What's the probability that a randomly selected woman is taller than 61%? I'm starting to get a little busy here, but let's see. Taller than 61 would be from the 61 mark over. So I've got a 34%, 34, a 13.5, a 2.35, and a 0.15. So if I add all those together, and they're all percentages, that gives me 84%. Now they could also ask me the other way where they say, well, what's the height? So that only 2.5% of women fall below. So they could ask me, go to where you see below being 2.5%, that'd be this, everything below this height. There's only 2.5% of women below 58 inches. Okay, so anything lower than that would be considered unusual, like on the low side of heights. What is the height that only 0.15% of women fall above? So here's my 0.1% here. Above that, so above 73 inches, so only 0.15% of women are taller than 75 inches or 73 inches. And finally, what is the z-score for a woman who is 64 inches tall? So that happens to be 64 inches happens to be our mean, so you may know this already, but just as a reminder, how do we calculate z-scores? We take the value in question, so 64 in this case, minus the mean, which also happens to be 64, divide by the standard deviation, which is 3. So in this case, we get 0 over 3 or 0. So a z-score of 0 is the mean, right? Because if we were going to standardize this information and use a standard normal graph for it, 64 would be the mean. Standardized, the mean is always 0. And then any other value would turn into 67 would turn into a 1, 70 would turn into a 2, 73 would turn into a 3, because these would be telling us we are 1, 2, and 3 standard deviations above the mean. And 61 would turn into a -1, 58 would turn into a -2, and 55 would turn into a -3, since these are 1, 2, and 3 standard deviations below the mean. And you can all check those out. You can calculate them if you want to double check, but that's what it means to standardize any situation. It just means to go ahead and recalculate and put all the values in terms of how far are they from the mean instead of what their actual number values are.